Okay, so I'll bore you once more with, I'll repeat for the people who have not attended. So we are discussing variational inference. We want to compute the posterior distribution, known the likelihood and the prior. The product of the likelihood and prior is sometimes intractable because the denominator is the evidence, which involves integration and might be computationally complex. We want to approximate it. Our way of approximating it is basically restricting a set of approximators Q to a set script Q and finding out the closest approximation to p theta given x among these set script Q. The closest is measured by the Kullback-Leibler distance between Q and P. The Kullback-Leibler distance between Q and P. So our optimization problem is minimize KL divergence between Q and the posterior, given theta varies over script Q. And this is still difficult to compute because p theta given x is still involved. What we do is that we expand the evidence, and if we do this algebra, evidence becomes the sum of some lower bound L of Q theta plus the KL divergence between Q theta and P theta given x. This L is called the ELBO, and we have shown that the sum of this ELBO divergence between Q theta and P theta given x is a constant log of Px, because this is independent of Q. So minimizing KL divergence is equivalent to maximizing the ELBO. So we have our new optimization problem, which is maximize over Q over script Q, the ELBO function. And if we expand the ELBO, we saw that ELBO becomes the sum of the expected value of log of P of the likelihood with respect to Q, distribution Q, and the KL divergence between Q and P, the negative of that. We had some nice prior and likelihood combination explanation for this. But the point is that this function, this ELBO function, because P, the likelihood and the prior are known, this is computable. And at least the objective function can be computed. We'll see that given this computability of the new objective function, we can devise an algorithm to maximize it, which will minimize the KL divergence, the approximation factor. So there is a nice statistical physics interpretation of this ELBO. It's like this. If we look at x as something kind of a temperature and theta as something kind of a enthalpy or pressure, then this is kind of entropy plus an energy. This is kind of energy of a function, log of the thing. And this is, as you know, is the classic definition of entropy of the distribution. I think all of you know the definition of entropy. I think we'll use it. So let me quickly mention what is a entropy of distribution. The entropy of a distribution is like this. Suppose there is a distribution D over a domain X, and D takes on several values. Let's say initially consider discrete values. So D takes on a value, X rather takes on a value x1 to, let's say, xk. And the probability of X taking on any of these values is, let's say, P1, P2 up to Pk. So entropy is a property of a probability distribution. If it is a discrete distribution, that means X takes on value x1 to xk, and their corresponding probabilities as specified by the distribution is P1 to Pk, then entropy would be summation Pi log of Pi, I equals 1 to k. Okay, so what this means, for example, if this was just a Bernoulli distribution, that means you have only two values, say head and tail, and the probability of tail is say p and the head is 1 minus p. Of course, we have the restriction here that summation pi has to be equal to 1 because it is a probability distribution. So if it is a Bernoulli distribution having value p and 1 minus p, entropy would be p log p plus 1 minus p log 1 minus p. Okay, so if p is either, so p is the bias in the coin. You can think of it as a coin toss. So if the bias is fully biased, that means you have p equal to 1 or 1 minus p equal to 1, which means either it's the deterministic, either head comes or tail comes, then the entropy is minimum. Entropy is 0 actually in this case. Entropy is 0 if it is only head or only tail. There is no randomness. If it is completely unbiased, that is p equal to 1 minus p equal to 0.5, entropy is highest. Okay, so entropy is highest. Often instead of entropy, we also, because see log p is less than 1, so log p would be negative. So this entire quantity would be negative. So sometimes we put a minus sign here and call it as the negative entropy. So the entropy is kind of, more uniform the distribution is, more evenly spread the probabilities are over all possible values, higher the entropy is. And more concentrated the distribution is towards a particular value, or more, maybe more than one values, the less the entropy is. It's less away from stochasticity. It's more deterministic. Whereas if it is uniform, you have a high entropy. Everything is likely. You cannot predict anything about it. Everything is equally likely. If instead of a discrete case, if you have a continuous case where you have a continuous distribution over X, then entropy is kind of an expectation of not the expectation of the logarithm of X. So it is integral over the domain of X dx log of dx. Okay, dx log of dx with respect to. Okay, so this is the definition of entropy for the continuous case. Here also, the uniform distribution would have the highest entropy. In fact, there is a nice theory which we'll use later, is that every distribution maximizes. Note that this is not the only definition of entropy. You can. This is known as the Shannon entropy. You could have defined your entropy in terms of some other function also, but it's kind of likely. Note again that entropy is also a functional. It's a property of a distribution or a function. It gives a scalar value. So for as I have told, the uniform distribution maximizes this entropy. Similarly, there are other entropy distributions which are maximized by the Gaussian distribution. So given any distribution, you can also characterize a distribution by the entropy it maximizes. So if you take the Gaussian, there is also an entropy definition which is maximum for the Gaussian distribution. Right. So if you think of the space of all distributions, and if you think of a functional, every distribution is kind of a Q star. It optimizes the entropy, provided you have a proper definition of entropy. Okay, so this view, this maximum entropy view, this we'll use later in deriving some estimation algorithms. We'll derive later in this thing. All right, but you see this ELBO that you are getting is also kind of a entropy maximization technique. Okay, so it's kind of you want that particular Q which has sum of two which maximizes the sum of two quantities. Both are functionals. Sum of two quantity. One is the energy between of the joint distribution x and theta. where energy is defined this way, the joint distribution x and theta, and the entropy of Q. So this entropy of Q is kind of a, this should be a minus here. This should be a minus here. Hello. Okay, so the entropy of Q, again, this is a kind of a regularizer. So you want to maximize the energy, and also you want to minimize the entropy. Okay, it's kind of a regularizer. Okay, so the sum of this quantity is sometimes known as the variational energy or the Helmholtz free energy in statistical physics. So there is a big body of research which derives all this variational inferencing and everything using notions of statistical physics, which are kind of intuitive and easy to visualize. This L also is sometimes in the, if you look at it as a variational calculus problem, this L is also sometimes known as the Lagrangian. It's a very important quantity used in solving variational calculus problems. Okay, anyway, we'll not go into all those. We'll just have a computational algorithm to maximize this ELBO. We just need a computational algorithm. Right. So our optimization problem, as I have showed, that maximize Q over script Q, maximize L such that Q varies over script Q. And why are we in the first place doing is that is because this P is intractable. We choose a small subset of all possible distributions, which we call script Q, with the consideration that this script Q is tractable. It's easy to, in some sense, it's easy to compute. And we get the best approximation among this subset for P theta x. So now let us concretize what is the meaning of this tractable or nice. So we'll see what classes of script Q are good for us, the one that we'll choose for our approximation. Okay, so we'll mention some properties of script Q and then see why these properties are useful for solving the maximization problem. Okay, there is one more thing, let me quickly mention, is that we have used KL divergence as the approximation factor. In general, you can use any other distance, or not distance, the similarity between two distributions. In general, you can use, it is actually quite popular recently, you can use a notion called an alpha divergence. In fact, there are further notions called the breakband divergence and other things also. Its alpha divergence is you have a hyperparameter alpha, and the divergence between P and Q is some constant, and 1 minus the integral Px raised 1 plus alpha by 2 and Qx raised to the power 1 minus alpha by 2, integral over all x. Okay, so this also, when P equals Q, this is 0. And also this is not symmetric, but it's not a metric. This is a general form of the KL divergence. If you make alpha goes to 1, it becomes KL. And if alpha goes to 1, it is KL from P to Q. Note the directionality. It is not symmetric. If alpha equals 1, it's P to Q. If alpha equals to minus 1, it's Q to P. So we are more interested in alpha equal to minus 1. We are more interested in Q to P. One question you may ask is that why you are choosing Q to P? You can as well choose P to Q. That means you can set alpha equal to 1 in the alpha divergence. This is used there is an algorithm called expectation propagation, which is an alternate to variational inferencing. It's called expectation propagation. It's more close to the EM algorithm, uh, which also is a way of approximating distributions. So instead of choosing your distance function at KL Q to P, you choose your distance function as KL P to Q. And people have used it. Only thing is that it is computationally not so nice as KL Q to P. It's more complex, but also it gives a good approach. Sometimes it gives a good approximation. And if you set alpha equal to 0, you get a symmetric KL divergence, sometimes called the Hellinger distance, which is like this. It's called the Hellinger distance. Also, there are approximation techniques. There are variational inference techniques which use the Hellinger distance instead of the KL divergence between Q and P. Okay, so these are taken from this book, the textbook. There is a modern research involves discussion on many of these. Okay, so here is a summary. We want to optimize, maximize this ELBO such that Q varies over a particular set, which we'll study next. What set Q varies over? All right. Also, I would like to make a point here is that so far we are talking about finding the best parameter. So we are talking about posterior of theta given x. Theta, the parameters given the distribution, and the ELBO is a function of Q, where Q is a function of Q is over theta, is a distribution over theta. In general, this theta need not be just the parameters. It need not be just the system parameters, because so far what we did was we did not consider latent variables. We just considered a kind of a generative distribution. There is a set of parameter theta, and you are generating a variable x, and we are fully observing the variable x. In general, you can have latent variables too, or you can have outputs too. You can have latent variables too. So in general, you can have another z, which is not observable, and you might be interested in the posterior p theta as well as z given x. You might be interested in estimating both the joint distribution of the parameters as well as the latent variables. I think we discussed before that the line between latent variables and parameters is kind of thin. So the parameters are sometimes called global variables, whereas latent variables are kind of local variables. And it's not entirely sure what is local, what is global in many of the models. In some of the models, they are clear. So, is that we'll club together, we'll assume that there is some local z as well as some global theta. We'll club these two and call them as parameters z, and call them as z itself. Okay, and all this discussion we had so far, about constructing the ELBO and maximizing it, they do not change much if we also introduce a latent variable set. Okay, so I'm not repeating, but those discussions remain. So from here onwards, just to get you familiarized, just to make you feel that these are actually the same, we'll use Z. All right. So now let us look at the class of script Q, the class of approximating distributions, what properties we desire out of it. We will say that Q, we will say that our Q we want to find the best approximation. Our Q is belonging is only a particular category of distributions known as factorized distributions. what it means? It means that if your parameters, if your latent variable plus parameters, which we together call Z, is partitioned into a set Z1 to, let's say, Zm, which is non-overlapping. That means, so now we are kind of doing non-black box. That is, we are looking into Z, what Z is. We are looking at the interaction between different parts of Z. Okay, of course, Z is a vector. So what we are doing is that the entire group of latent variables, we are partitioning them into M groups. Okay, how we are partitioning, we'll see later. Just I mentioned that it will be some kind of a natural partition. So we are partitioning the capital M number of latent variables. Sorry, we are partitioning all the latent variables, I don't mention here how many, into capital M groups. And these groups are non-overlapping. Okay, so it may be that these groups may be singleton groups. So every latent variable we look at as a separate partition, or it may be a vectorized group. That means Z1 may be a set of 3 variables, Z2 may be a set of 4 variables, and so on. But they have to be non-overlapping. We say a distribution Q is a factorized distribution if you can represent the joint distribution. Okay, so this is a joint distribution. Say Z1 to, if you have capital D number of variables, this is the joint distribution. This bold set is the joint distribution. This is a product of the marginal distributions restricted to each of the groups. So QIZI is the marginal distribution restricted to the ZI partition, Okay, so this need not be a single Z. This may be a vector Z itself, but it's one of the partitions. So if Zi is the, we restrict Q to only over Zi. So we do a marginalization basically. We do a projection. We do a marginalization, and your full joint distribution is product of these marginals over the partitions. It's a product of these marginals, right? So I think it sounds familiar because in the naive Bayes classifier, we did the same thing. We assumed that the full joint distribution is product of the individual marginal distribution. Only difference is that in the naive Bayes, each of these Z1 to Zm were singletons. They are single variables. Okay, but in general, in factorized distribution, they can be a group of variables. I think those who have studied Bayesian network will see that in Bayesian network, these Z1 to Zi are actually sometimes group of variables known as Markov blankets. Okay, so we are going to restrict our Q to only factorized distributions. Note that we are not making any assumption about the parametric form of each of these QI. They can be anything. They can be Gaussian, they can be gamma, they can be anything. We are not making any restriction. So that's a better thing to do. We are not making any distribution assumption. Only thing we are assuming, so it's kind of an assumption on the latent variables. We are kind of saying the latent variables are decoupled from each other. They are independent of each other. Remember that when can we do name base? When each of the variables are independent of each other. So this factorization is kind of a independence assumption or non-correlation assumption among the latent variables Zi's. Okay, it's not an assumption on the functional form. Also note that all these assumptions are only on Q. We are not making any restriction on what we can approximate. We can approximate anything. We are not making any restriction on P. We can approximate anything, but we'll approximate it using only factorizing distributions. We'll approximate it only using factorizing distributions. That's our restriction. And we'll do this. We'll see that the ELBO maximization problem can be solved for the factorized distributions easily. It can also be solved for some kind of non-factorizable distributions also, but for factorized distributions, it is very easy to solve. Okay, so I'll maybe try to give an. So this kind of distributions, which are okay, let me try to explain it this way. Let me take a slide here. Let me try to explain what these factorizing distributions actually mean. So let's take the simple case. So I have two variables, Z1 and Z2. And let us look at the full posterior. Okay. And let's assume to be a bivariate Gaussian. We are trying to understand what kind of restrictions or what kind of loss we make by assuming these factorized distributions. Okay, so this let's say it is a full Gaussian. So let's say Z1, Z2 is distributed according to a normal distribution, say 0 or mu1, mu2 mean, and some covariance matrix of this type. Okay, let's say this is the full, very simple case, but still it will illustrate. It's the full posterior looked like this, and this is what we are going to optimize. Well, maybe you don't need to approximate it, not optimize. You need to want to approximate. We don't need to approximate it, but still, nevertheless. So what happens if we drew the contours of this bivariate distribution? So this is Z1, this is Z2. This distribution, let me call as P. In general case, for arbitrary values of sigma 1, of course, this has to be positive definite and all those conditions are there. This distribution would have contours something like this. Okay, so equal probability contours. Let us look at another distribution, Q, which is product Q Z1, Z2. So this is my approximation of P. Z1, and this is a factorized distribution. Okay, so I am the approximating joint distribution Q is a product of two univariate distributions, and give some form to these univariate distributions. Let's say it is n mu1 sigma 1 and Q2 is n mu2 sigma 2. Okay, these are the individual factors of Q. Now, if we multiply these two, normal distributions, just write the e to the power x minus mu1 by sigma 1 square. If you do the multiplication and then just combine the exponentials, you will see that Q Z1, Z2, if I do this multiplication, becomes a normal distribution with mean So bivariate normal, mean mu1, mu2, and a covariance like this. Okay, so what effect this factorization had is to remove the correlation between Z1 and Z2, remove the off-diagonal elements of the covariance matrix. It removes the correlation. Okay, so now you can change your mu1, mu2, you can change your sigma 1, sigma 2, 2, but the form of the distribution has this restriction that off-diagonal elements are 0 in the covariance. Right, so you will actually with 100% accuracy never be able to approximate this by this, because you have lost this. Okay, but we are ready to lose them, because this factorization has some computational advantages. So we are ready to sacrifice these off-diagonal terms, but that's all we can do. That's why it's an approximation. What does it mean in terms of the contour plots? It means that, note that these off-diagonal elements kind of allow distributions which are not axis parallel. Okay, so if you don't allow these off-diagonal elements, they become something like this, which are kind of axis parallel. This is your sigma 1, 1, and this is your sigma 2, 2. Okay, this is sigma 1, 1, and this is sigma 2, 2. Right, so you don't have inclined distribution, oblique distributions. So this is a restriction. This is a restriction. In fact, if these two distributions, if sigma 1, 1 was equal to sigma 2, 2, then it would be a kind of a circular thing. Okay. So this, of course, this is often not a good approximation, but actually it's not so bad a approximation also. It's not so bad an approximation also, because suppose I approximate it by something like this. You see, since it is a normal distribution, the high density region of the normal distribution are near the mean. So this part is the high density region, and that part is well approximated. Whereas this part, these are the low density regions, and there is more mismatch in the low density regions, which is actually not so bad. If in terms of the Kullback-Leibler distances, you see Kullback-Leibler gives more importance to the differences in the the similarities in the high density region. Okay, so it's in terms of Kullback-Leibler, this is probably not a very bad approximation. So, but of course, it's one more point to be noted is that I cannot, moment I do this factorization, I cannot fully accurately approximate the original distribution. There is always an error. It's not like an universal. It's not that arbitrarily close I can go Z1, Z2. Okay, there will always be a good amount of error which you cannot reduce, whatever you change your Q1, Q2. Okay, one more thing. Note that this may not. I have just assumed Q to be of this form. Okay, there is. I have not taken any step to ensure that this Q is actually the best factorized approximation of P. I am not assuming that to be the best factorized approximation of P. Okay, I have just assumed some form. So in this case, it turns out this is probably the best approximation. But how do you do the best approximation? How do you do the best factorized approximation? Okay, so let me tell you a technique which will actually motivate the full formal technique. The thing is like that. One way of doing this factorization, so I want to Find the optimal factorized approximation of this target P. So what I do one by one. I fix my Q. I fix my Q2. I fix Q2 and just change Q1. In other words, I first find the best. If my Q2 was constant, what is the best Q1 that approximates P? So this is P. You find the best Q1 that approximates P. It turns out if you solve an optimization problem and all those things, so Q2 is fixed. Vary Q1 to find best Q1, Q2, because we are approximating it by Q1, Q2. Okay, as it turns, it will turn out that if we do this, probably the best Q1 would be something like this, maybe. Okay, so now you fix Q1. Now keeping Q1 fixed, you vary your Q2 so that it's the best approximation of P. So now you make your Q2 maybe, so this is your Q1 and this is your Q2. Note that they are one-dimensional distribution. So this is your Q2. Okay, so keeping Q1 fixed, maybe this is the best Q2. And then after this single iteration, Q1, Q2 is the best approximator. And then you repeat. Then again you alternate between this. Then after finding Q2, you fix Q1, fix Q2 again, find the best Q1. All right, and then fix Q1 again, find the best Q2, and iterate. Iterate, starting from some arbitrary distribution. And if you do this long enough, you will get the best approximation. You will get the best approximation. So this method is known as the method of block coordinate ascent. In this case, it is coordinate ascent because we are changing one single coordinate, one single Q, one single factor, keeping the other factors constant. Okay, and we'll now in the next lecture, in the next part, we'll derive the by solving some derivative and all those things, we'll find the best Q1 approximation to P. Okay, so if this Q1, Q2 are single dimensions, we call it the coordinate ascent. You fix all other coordinate, change only one coordinate, where each factor is can be thought of as a coordinate. If they are fully naive, that means every single factor is a one single Z1. It's coordinate ascent. So you fix all the coordinates except for one, change that. Now move over, keep that and everything else constant, move to the second one and change that. And cycle over all Z1 to Zn. If Z1, Z2 are not single coordinates, but they are blocks of coordinates, they are groups of coordinates, this is called the block coordinate ascent. This is an optimization problem, optimization method. And note that I can apply the block coordinate ascent only when this Q can be factorized. Only when Q can be factorized, I can apply this block coordinate ascent. Okay, so we'll derive the update rule for the block coordinate ascent. So update rule, basically you start with some Q1, Q2, Q1 0, Q2 0 up to Qm 0, keeping everything else same, vary Q1 to get Q1 1. So what is at every step of the block coordinate, you get Qt plus 1 I as some function of Qt over all I. So that's the update rule, how you get a new distribution at every iteration and repeat it till it converges. Okay, so we have seen so far that in these factorizing distributions, you can apply a method of ELBO, a method of block coordinate ascent to optimize your ELBO. We will. I say that you find the best approximation, but best approximation is equivalent to that Q which maximizes ELBO, minimizes the KL divergence. Okay, so this factorizing distributions are also not also, they are actually called the mean field approximation. They are called the mean field approximation. Okay, so this Q would be this factorized Q would be a mean field approximation of P. It would be a mean field approximation of P. So this entire topic we study next is called mean field Bayesian inference, mean field variational inference. Okay, so this mean field is a well-known theory in physics. The idea is something like this. Let me try to explain. Suppose I have, say, a crystal or something. I have some molecules, magnetic molecules in a crystal, arranged in some kind of a lattice. You know, crystals take the form of a lattice. I'm explaining a physics problem, but it's probably more applied to data science problems than physics problems. So every molecule in the lattice has a magnetic spin, which is up or down, plus or minus. Let me call. I can also call it 0 or 1. And the spin of a molecule is determined. It determines on its magnetized state, and which again is determined by the magnetized state of the other molecules in the lattice, because they will influence by a magnetic field. They will influence. So the problem is that if you give such an configuration of lattice, and if you initially magnetize it, sometimes there is an external magnetism also put from above or something, external magnetism also. The question is that you have to find the steady state distribution. So let me define some terms. So each of these point, let me call them as x1, x2, x3 up to xn. These are molecules, and each of the xn has a magnetizing state, which I call, say, sigma 1, sigma 2 up to sigma n. So sigma I is a random variable which can either be +1 or -1. It's a random variable, nevertheless. So it's a collection of variables x1 to xn. It's a collection of random variables x1 to xn, where each of the random variable we denote by sigma I, taking on value +1 or -1. And the state of the system would be the collection of all these random variables. We call it a state of the system. So in general, if you want to find out the state of a system, it's a multi-body problem. That means you have to take note that the state of the system can be thought of as a magnetic field over this lattice. Can be thought of as a magnetic field over this lattice. It's a value of the magnetism at different points. Okay, so in general, if you want to find this field or a state, it's a very difficult problem. It's a multi-body problem where, say, x1 interacts with x100, x3 interacts with x20, and so on. Everybody interacts with everybody because it's magnetism. You have a magnetic field spreading all over the universe. So it's difficult. It's a multi-body problem. You'll have very complicated equations, and it may be pretty impossible to solve it. So what the mean field theory does, it does an approximation. It converts this problem of finding the field in a multi-body problem of finding the field into a two-body problem in the following way, but not a single two-body problem, a family of two-body problems. How do you do it? It's like you take any one xi, that is one body, and everything else is the second body. Everything else is the second body. Okay, so xi is one body and everything else is the second body. And the multi-body problem is approximated by the integration, the interaction between xi and xj I not equals j. Okay, xi and xj I not equals j is the interaction only between two bodies. And so this interaction is kind of a mean or an average interaction over all xj I not equals j. So everything else, xi with everything else is approximated by this mean interaction, not a collection of interactions. They are aggregated and form the mean interaction. Okay? So they induce a kind of a mean field over xi. So, so maybe you can have things like this. You can have, yes. So xi, the field over xi after one interaction is determined by some constant j, and the interaction of xi with only neighbors. So I can define my neighbor in whatever way I want. Maybe just the adjacent molecules or something, or maybe molecules within 1 micron of each other. Okay, so this is the so you have a kind of strength of interaction between. So just this may be product. So if xi is +1, xj is +1, their product is 1 multiplied by j. Or if xi is +1, xj is -1, they have a negative interaction. It's -1 multiplied by j. So this summed over all the neighbors, the sum of the mean interaction with all the neighbors. Well, this is an approximation in the sense that I am taking only the neighbors. I am not considering the entire universe. Plus, sometimes there is an external magnetic field which is there over all the xi's. Which is there over all the xi's. So there is an external magnetic field. And this external magnetic field plus the local interactions determine your xi. So this is a kind of approximate solution to the original multi-body problem. This particular model is called the Ising spin model. Ising spin model of magnetism. Okay, so in general, this can be more things. Say for example, I have an image. Let's say I have an image, a binary image. Let's say a character recognition problem, character where the values are either 0 or 1, a binary image, and you can have a mean field description of a binary image. Say the value of a pixel is determined by the probability of a pixel taking on value 0 or 1 is determined by the probability of the neighboring pixels plus some overall brightness term or something like that. So this can as well be a model for image generation. This can as well be a model for image generation. Or not only image generation, usually mean field is very much used in image denoising. So you have an underlying model of an image and you want to remove the noise. So you take this kind of mean field interactions and settle down. So what finally is that how xt plus 1 gets integrated is that you make xt plus 1 with 1. So this is called a field or energy. Not field, this is called the energy of this particular configuration. You make xt plus 1 equal to +1, see what is the energy, makes xt plus 1 equal to -1, see what is the energy, and you choose the one which gives a lower energy because the entire thing wants to settle down to a lower energy. Okay, you choose, so if -1 gives a lower energy, you make it -1. So that's the new value of magnetism at that point. Okay, so similarly in images, so this process if you carry on, there is often a denoising that goes on. It's kind of averaging. Okay, so this is a very popular theory used in many places. The underlying probability, but it is basically a probability theory. It's basically how does probabilities get influenced each other, even though it is used in statistical physics. So say over distribution of gas molecules or something like that. And the underlying probability is that of factorized distribution. The probability distributions are basically factorized. So I said that these are random variables. So the final configuration is kind of a distribution over these random variables. So we are in the full multibody case, whatever the distribution is, we are approximating it by the distribution that you get by this mean field approximation. Okay, so that's why it's called the mean field approximation. So the factorizing distributions henceforth will be called mean field approximations, and we'll call it mean field variational inference. It basically means if your Q is restricted to this class, and then if we do ELBO maximization, what you get is variational inference. And the method to solve it, I have already explained, is called the block coordinate ascent. Let me take a quick break, and then I will come back and describe the block coordinate ascent method. I will come back at 9:20.